Our second lecture will focus on the history of evolutionary theory. But before we get to that, let's think a bit about some of the commonly known facts about the history of science in general. True or false? Before Christopher Columbus, all educated people believed that the Earth was flat. That's false. All educated people have known since at least the 3rd century BC that the Earth was round, when the Greek scholar Eratosthenes calculated the circumference of the Earth to 97% accuracy. True or false? Before Galileo, all educated people believed that the Earth was the center of the universe. Again, false. The heliocentric or sun-centered model of the solar system was introduced to European astronomy by Copernicus. Galileo was just a vocal supporter of Copernicus' work, and Copernicus was actually just reviving the theory of Aristarchus of Samos, another 3rd century BC Greek. So true or false? Before Darwin, all educated people believed that all of Earth's species were created by God in their current forms in 6 24-hour days. False. At that time, the Earth experimented with the creation of many prodigious things, but they were created in vain since nature denied them growth and they were unable to attain the coveted bloom of maturity or find food or be united in the acts of Venus. Many species of animals must have perished and failed to propagate and perpetuate their race. For every species that you see breathing, the breath of life has been protected and preserved from the beginning of its existence, either by cunning or by courage or by speed. But those animals that nature endowed with none of their qualities, so that they were unable to be self-supporting, were of course an easy prey and prize for others, shackled as they all were by the bonds of their own destiny, until nature brought their species to extinction. That was written by a Roman scholar named Titus Lucretius Carus in 54 BC. You'll find, frankly, that many of our popular notions about the history of science and human thought are wrong. Most so-called scientific revolutionaries were actually working within a fairly large community of like-minded scholars building on the work of their predecessors. We like to tell the story of the lone maverick who refuses to accept common wisdom and brings truth to a benighted and ignorant world, but that's just not how science usually operates. As Isaac Newton, one of the founding fathers of the scientific revolution, said, "If I've seen farther than others, it is because I stood on the shoulders of giants." By the way, Isaac Newton was never hit in the head by a falling apple. What we'll be talking about today is the history of evolutionary thought, the real contributions of Darwin, and where those ideas come from. Contrary to what popular wisdom would have you believe, he did not invent the theory of evolution alone. Much of Darwin's genius was not so much in creating new ideas as it was in rearranging the ideas of others into a more accurate way of describing the world around us. And that's an important idea to understand because the work of a single scientist may be flawed, but the work of hundreds of scientists spread across centuries is much less likely to be so. To begin, we need to go back to the 17th century, when scholars were often still clerics, and science, as we would recognize it, was only just beginning to separate itself from theology. Most so-called scientists still considered their job to be to demonstrate how God had structured his creation. At this time, most learned people did still believe in the fixity of species, the idea that species were created by God in the 6 days of creation, and they had not changed since. One reason they believed this was that it was church dogma, not believing it could get you into real trouble, but also because of the patent evidence of their own senses. That, by the way, was the real contribution of Galileo to science, the idea that your own senses should be trusted as evidence of how the world works. When you see a horse today and look at a horse from the last generation, they look the same. When you look at pictures of horses from the ancients, they look the same. When you breed 2 horses, you get a horse that looks pretty much like both of its parents. Now, everyone did understand that you could control breeding for particular characteristics, but those were very small changes like color. They also understood you could accumulate a series of small changes over many generations to make bigger changes, but that would take an extremely long time. And that was the sticking point. In the 17th century, no one, not even the highly educated non-religious types, believed the Earth was old enough for significant change to accumulate. It was not uncommon for scholars, even those we wouldn't consider theologians like Isaac Newton, to analyze the Bible and calculate that the Earth had been created in only about 4000 BC. The most familiar of these calculations today was the one made by Bishop James Ussher, an Anglican bishop from Ireland. He believed that the moment of creation had been the evening before Sunday, October 23rd, 4004 BC. Since this was about AD 1650, the Earth was therefore only about 5,600 years old, much too short for any sort of significant species change. So the work of Ussher is something of a starting line, a 0 point, at which time there is no evolutionary theory. In fact, the best, most reliable scholarship of the mid-17th century said that not only did evolution not occur, but that it couldn't have occurred. The very notion seemed silly to 17th century scholars. Things didn't change quickly. In fact, almost 200 years passed between Ussher and Darwin's theories. But things did start to change soon after Ussher's day. The first significant development was the concept of species. John Ray, in the late 1600s, proposed that animals could be categorized according to their reproductive behavior. That is, species are reproductively isolated. They cannot interbreed with members of other species and produce fertile offspring. Does that mean no one understood that horses and dogs were different before Ray? Well, of course not. And they didn't think that horses could interbreed with dogs either. What Ray did was remove God from the definition. Prior to this time, different kinds of animals were considered to be different because they were the products of different acts of creation by God. Horses were not dogs because God had created horses and dogs in two separate acts. Ray defined species without appeal to a supernatural agent. He did not deny God's role in creation. He simply pointed out that we didn't need to mention God to distinguish one species from another. Scholars could now begin thinking of how biology works in purely natural, not supernatural ways. This set the stage for the next development. That came in 1735 with the publication of Swedish scholar Carolus Linnaeus' Systema Naturae. Linnaeus' insight was equally unspectacular, that some animal species were similar to one another and others were more different. He proposed that species could be categorized into larger categories based on how similar they were. He created the ancestor of the hierarchical system that we still use today to classify living things: kingdom, phylum, class, order, family, genus, and species. Linnaeus' system was purely descriptive, however. It didn't try to explain why species had the relationships they did. In fact, Linnaeus was committed to the fixity of species. He still explained those differences and similarities by simply saying, God did it that way. But what Linnaeus did was provide a hierarchical system that suggested that even if species were reproductively isolated, they still had some sorts of relationships with one another. One other major addition Linnaeus made was to include human beings in his system as Homo sapiens. This was rather radical at the time, suggesting that humans could and should be studied as just another member of the animal kingdom. Many would have considered it heretical. Linnaeus' work set the stage for people to try to explain those relationships scientifically, and not everyone was committed to fixity of species. The next player is Georges-Louis Leclerc, Comte de Buffon, who's obviously French. Buffon was not so committed to fixity of species. In fact, he believed they changed over time. He recognized that environment had something to do with species traits. Closely related species often lived in similar environments, and many animals in the same environment had similar features. But he stopped there. Linnaeus raised the question, why are species similar to one another? Buffon answered, it has to do with the environment, and left it at that. Now we're in the late 18th and early 19th centuries, and another Frenchman, Jean-Baptiste Lamarck, answers the question that Buffon didn't. Lamarck suggested that species changed as a result of how they interact with the environment. Those parts of the body that are used will strengthen and develop, while those parts of the body that were not used would wither and vanish. Thus, Lamarck's theory is often called the use-disuse theory of evolution. The classic example of Lamarck's theory is the giraffe. He said giraffes had started with short necks, as most of the otherwise similar species relatives have. They ate low leaves off of trees, but then couldn't reach the higher leaves, so the giraffe stretches his neck to reach the higher leaves, and over the course of many years, this exercise stretches his neck permanently. When that giraffe has offspring, They're born with longer necks. The basic tenet of Lamarckian theory was the inheritance of acquired characteristics. Traits that a parent acquires in life, he or she passes on to the next generation. There's a big problem with this theory, which is obvious in hindsight. By this theory, Arnold Schwarzenegger's children should be exceptionally strong, and disabled vets should have children with missing limbs. But so long as Lamarck and his contemporaries were only applying the theory to exotic animals from far-off places like Africa or the South Pacific, the inheritance of acquired characteristics made sense to them. Lamarck also believed that all animal species always change to become more complex and sophisticated over time, and that new, very simple life forms were always springing into existence out of non-living materials, so he got a lot wrong. But what he did do was give us another piece of the puzzle. Species changed because of how they interacted with the environment, and not because of the environment itself. And reproduction and inheritance had a lot to do with it. One other French theorist is important here, and he was Lamarck's biggest opponent because he was firmly committed to the fixity of species. How then could Georges Cuvier be important at this stage in the story? Well, Cuvier believed that species did not change, but he was also an expert on fossils. He saw that, beyond any doubt, there were fossil species that did not represent any living animals, and living animals for which there were no fossils. Cuvier invented the idea of extinction to explain it. Animal species didn't change, but they did appear and disappear. But why did they do that? To answer that, Cuvier promoted the idea of catastrophism, the view that the Earth's geological landscape is the result of violent cataclysmic events. These cataclysms were unpredictable and didn't obey natural laws, being ultimately the result of God's direct action on the Earth. Cuvier believed that these cataclysms wiped out most living species, which were then replaced afterward by species newly created by God. Species were fixed and unchanging in between cataclysms. Now, clearly, Cuvier's theories are no longer held by most scientists, but he is interesting because his is really the last serious scholarly attempt to integrate the supernatural into a systematic scientific understanding of life on Earth. And he did give us something that earlier scholars hadn't hit on, that species are always appearing and disappearing. All of this theorizing about evolution was taking place in a scholarly environment that still believed in a very young Earth. Though many scholars were not sure about fixity of species, they still had no good reason to disbelieve calculations like Usher's of a 5,600-year-old world. So while they believed that species could change, most scholars still didn't believe they could change that much. The next part of the evolution puzzle comes from an Englishman who wasn't even a biologist. Charles Lyell was a geologist who is often considered the father of modern geology. In the 1830s, he published Principles of Geology and demonstrated that the Earth was at least many millions of years old. He did this by popularizing the concept of uniformitarianism, which is every bit as important an idea to modern science as natural selection is. Uniformitarianism, in Lyell's sense, says that geological processes in action today were also in action in the past, and those processes had the same effects in the past as they do today. All of the Earth's geological features can be explained by the continual functioning of processes like erosion, sedimentation, etc., just extended over millions of years. More generally, you can say that uniformitarianism says that any modern process could also have happened in the past and would have had the same results. Uniformitarianism thus gives us two major points to the development of evolutionary theory. First, that there has been plenty of time for really substantial changes to animal species. Second, we can study what happened in the past by looking at what's going on right now. One last building block before Darwin comes in and ties everything up in a neat little bow. And for this, we need to go a bit backward in time. That's the work of Thomas Malthus in 1798, an essay on the principle of population. Malthus was also not a biologist. He was writing about how and why human populations grow or shrink. He would have been called a social scientist today. But what he recognized is this: when two parents have a family, they usually have more than two children. If every family has more than 2 children, then the population grows geometrically every generation. That is, if generation 1 has population X, generation 2 will have X times Y, generation 3 will have X times Y, and so on. Population thus has the potential to grow very fast. But food supplies don't grow nearly so fast, and especially in the 18th century, the population was already right on the edge of what could be fed. New technologies and trade could increase food supplies, but not nearly so fast enough to keep up with potential population growth. So why hadn't everyone starved to death long ago? Because when more people were born than could be fed, famine would kick in and kill off the excess population, or an epidemic would break out, or, and this is the most important one for understanding Darwin, a war would break out, killing off many people. Why is any of this important for understanding evolution? Well, because as Darwin later recognized, it applies to any species, not just humans. There is always the potential to have more individuals born than can be fed in a given environment. This is called carrying capacity, the population that a given environment can support. Populations tend to hover on the edge of carrying capacity, and because of the stress of finding enough food, there's always competition over the resources that are available. That competition is called war among humans, but it's just as obvious in the animal world. So, after all this time, we finally come to Charles Darwin, born in 1809, died 1882. The outline of Darwin's life is covered fairly well in your textbook, so I'm not going to give you a biography here, but be aware, though, that you'll be responsible for the information in your textbook when the exam comes up. What Darwin actually did was recompile the ideas of these other scholars, combining them in new and innovative ways, and making some contributions of his own to explain why species change the way that they do. He called his theory natural selection, which can be defined as a change in the frequencies of certain traits in populations due to differential reproductive success between individuals. That is, since some individuals have more offspring than others, the traits they pass on to the next generation become more common than other traits. Why that happens, and the meat of the theory of natural selection, is due to the interrelationships of ideas established by many of the scholars we've been discussing. Pages 38 and 39 in your textbook explain this theory of natural selection in 8 points. Reproduction outpaces food supply, which is an idea drawn from Malthus. Number 2, there is variation in all species. And this one is one of Darwin's own contributions, really. Point 3, there's always competition for scarce resources. That comes from Malthus again. Point 4, better adapted individuals have an advantage. This comes from the work of Lamarck. Point 5, environments determines who is better adapted. And this one is Buffon's idea. Point 6, traits are inherited, Lamarck again, with differential reproductive success. That's another Darwin innovation. Those who do not reproduce die out. Cuvier with bits of Malthus and Darwin thrown in. Point 7, differences accumulate over long periods of time. That's Lyell's contribution. And they accumulate to create entirely new species. That's Cuvier again. And point 8, geographical isolation also plays a role, and that's something that Buffon talked about. So of those 8 major principles defining natural selection, Darwin himself only originated a couple points. The rest were ideas he drew from the large community of evolutionists who came before him. Darwin's Origin of Species was published in 1859, mostly because of the work of Alfred Russel Wallace. Wallace, a younger scholar, had developed essentially the same theory independently of Darwin. In 1858, the two arranged to share credit for the theory by each having a paper read before a scientific society. Then Darwin, the older, wealthier, more established scholar, published a book-length treatment, and Wallace's book followed a few years later. Because Darwin did develop the theory first, and because he did publish first, today we remember him as the originator of the theory of natural selection. However, it's a testament to how much Darwin was a product of who came before that Wallace came to almost the exact same conclusions totally independently. Darwin was first, it just It's just that he wasn't the first by much, and had he not published, Wallace would have soon enough. However, when he did publish, the book already had a mountain of irrefutable evidence. Many scientists of the day were immediately convinced, but a significant minority were skeptical. But contrary to popular belief, the average person on the street really didn't care. This was a debate taking place in academia, among scientists, based on data and theories completely foreign to most 19th century people's lives. It simply didn't matter to them. The furor came in 1871, when Darwin published The Descent of Man, a book on human evolution. People in general don't care whether finches and tortoises evolve. They care about themselves. It was the idea that we are subject to the same processes as so-called lower animals that got people angry. But that's a lecture for another class. In the interest of time, I'll pass over the last few pages of the textbook chapter, where the authors delve deeper into ideas of natural selection and offer examples of how it has been tested. Again, be aware that you will need to know that material for the exam. The last thing I want to touch on is the last thing the text touches on, opposition to the theory of evolution. The textbook does a good job of addressing this controversy at the end of the chapter and the reasons that objections to evolutionary science don't hold up. In this class, you will be required as part of the class curriculum to understand and apply natural selection principles without appealing to supernatural agencies. That's part of the requirements of the class. Just like knowing your multiplication tables is a requirement of third grade math. To pass this class, you have to understand evolutionary science, but I can't require you to believe it. It's not my place to force you to espouse or even believe anything outside this class, and you're well within your rights to reject evolutionary science if you so choose. But if you do so on assignments in this class, you will be marked down for it because this is a science class, and those objections are fundamentally not scientific. It's important to understand, though, that just because some idea is not scientific, that doesn't mean it's false. Many, I'd guess most, evolutionary scientists have faith in a creator who created the universe and set in motion its natural processes. This is a philosophical position called theistic evolution. It's just that we don't try to understand that creator with science, because science only deals with falsifiable statements, and one cannot falsify God. The method of science doesn't match the goal of learning about God. You don't use a screwdriver to drive nails, and you don't do science to learn about God. Let's stop here for this lecture. In the next lecture, we'll step forward to the present day to examine the biological processes that make evolution possible.